Hi everyone. Today we're going to talk about the solar system, or specifically our solar system, which involves our sun, which is a star, and all the objects that revolve around our star, which is the sun. So, in the past, we had a theory, and it's called the geocentric theory. Geo means Earth, and this theory involved us believing that all the planets or all the objects in the universe actually revolve around the Earth, and Earth is in the center. That's why we call it geocentric, Earth centered theory. And the ancient Greeks actually came up with this, such as Aristotle, and they believed this. The problem with this theory is that when planets were doing this motion called the retrograde motion, where planets temporarily appear to move backwards in the sky, the geocentric model couldn't really explain that. That's why eventually we came up with a new theory called the heliocentric theory. Helio means sun. So this theory is sun centered, meaning we think now that the sun is the center of our solar system, not the universe, and all the objects in our solar system revolve around the sun, including our Earth. Okay? Um, so this came up after we couldn't explain the retrograde motion, right? And Copernicus actually came up with this theory, and he made a model that could be used to predict future locations of planets as well. And he explained that this retrograde motion was happening because as all the other planets were revolving around the sun, different planets have different speeds and at which they revolve around the sun, right? And that's why other planets might seem like they're going backwards in our sky when the Earth is actually moving a little faster than those planets around the sun. So, and as a summary, geocentric models, this is our past model that we used to believe in. We used to believe that the Earth was the center of the whole universe and the sun and all the planets revolved around it. But now we believe in the heliocentric model, the sun centered model, where the sun is actually the center of our solar system and the planets revolve around the sun. So let's write this down in this part of your note packet. Go flip to this page. Our solar system is actually, we now believe, with a lot of evidence, is part of the heliocentric model, the sun centered model. And what is this? This is a model where the planets are revolving around the sun. So make sure you open page 15 of your reference table. It looks like this. And this is actually all the data for our solar system. So write this down as well in your note packet. Our solar system's data can be found on ESRT, page 15. So remember, celestial objects are objects that appear in space and that can be only seen through a telescope from Earth, or basically you can't really see them through the naked eye. So these are all the celestial objects within our solar system, and that includes the sun, it includes the Earth, and it even includes the Earth's moon. This little column right here shows the mean distance of all these celestial objects from the sun, and it's in millions of kilometers. So we don't have data from the sun because it's the distance from the sun, but notice that Mercury's distance is this many million kilometers, Earth's distance is this many million kilometers, and so on from the sun. Okay? And then for the moon, it tells us how far away the moon is from the sun. It also tells away how far away the moon is from the Earth in millions of kilometers. Next in this column, we have the period of revolution of all these celestial objects. And notice that D stands for days, Y stands for years. Some planets revolve around the sun, and it takes them 88 days or many days to go make one full revolution around the sun. But some planets take years to go around the sun. Okay? We also have the period of rotation. Remember, rotation means spinning, and the Earth is not the only celestial object that spins. All the other objects in our solar system also spin, including the sun, but they spin at different rates. And it shows you here. The sun takes 27 days to make one full rotation, one full spin. Mercury takes 59 days. Neptune takes 16 hours. And Earth takes 23 hours, 56 minutes, and 4 seconds. So it tells you how long each celestial objects take to rotate or spin. Next, we have the eccentricity of orbit column right here. And eccentricity of orbit is how close to oval or elliptical the shape of the orbit of a planet is. We said that elliptical is a shape that is not circular or close to oval, and elliptical shape is how we use to describe the shape of our solar system, right? All the objects that are revolving around the sun. Although some objects that revolve around the sun have a more eccentric orbit, meaning they're more elliptical or a little more oval, and some objects in our solar system have less elliptical orbits, meaning they're less circular. So elliptical is the shape, and the eccentricity of orbit tells you how oval or how circular the orbit is. So this is what this column is showing you, how circular or oval is the orbit, and the eccentricity or how circular or oval it is um, can only be a number between 0 and 1. The closer to 0 the number is, the more circular the orbit is, kind of like this red circle. And the closer to 1 the number is, the more oval the orbit is, kind of like this pink one. So notice that um, Mercury has a very small eccentricity of orbit. Its revolution or orbit around the sun is fairly circular, but something like, let's see. Actually, Mercury compared to the other planets have a more oval orbit. Say Neptune. Neptune has a much smaller number for the eccentricity of orbit. It's closer to 0. So compared to Mercury's orbit around the sun, Neptune's orbit is more circular. So the higher the number, closer to 1, the more oval, the closer to 0, the more circular. Next, we have a column of the equatorial diameter. This is the diameter of a planet at the equator. This also includes the sun, and it helps us determine the size of a planet or even a star. And just like any circle, the diameter is from one side to the other from the center, and we can use this to determine how big or small a planet is. And we have this in kilometers. So the higher this number is, the bigger your planet is. Next, we have the mass, and the mass is the amount of matter in an object. So hmm, in this case, it's not a real unit that we're using for mass. We're comparing the mass of different objects to Earth. So if Earth's mass is 1, then the sun's mass compared to Earth is times 33,000. And if the Earth's mass is 1, then Mercury's mass is zero point 0.6, and so on. So all these numbers are being compared to Earth if Earth's mass was 1. Lastly, we have density. And remember, density is how closely packed the mass is in a substance. And the higher the density, the more the object will sink. The lower the density, the more the object will rise. And it tells you the density of all the celestial objects in grams per cubic centimeters. And notice Saturn's density is less than 1. 1 is the density of water. So Saturn would actually float in water or rise in water because it has a lower density. Next, now that we know all these components or properties of the different planets in our universe, we actually classify the planets in our universe into two categories: terrestrial planets and Jovian planets. Terrestrial planets are the first four planets closest to the sun, and they're actually mostly made up of rock and metal. Jovian planets are much bigger planets that are farther away from the sun, the last four planets farther from the sun in our solar system, and they're actually made up of mostly hydrogen and helium gas. And this is because when our sun and our solar system was forming, most of the mass of space, dust, and gas were actually towards the center. That's why the sun formed first, right? And that's why, since most of our rocky, dusty parts, our mass was in the closer to the sun, we created more rocky planets like Mercury, Venus, Earth, and Mars. They're called terrestrial planets. Terra means Earth. The reason the outer planets, Jupiter, Saturn, Uranus, and Neptune, are mostly made up of hydrogen and helium is because a lot of that gas and dust that was here, a lot of that gas moved away from the sun towards more outer space because of sun's solar wind. And that's why most of the gases were here, forming our more gaseous planets called Jovian planets. So terrestrial planets are made up of rock and metal. Jovian planets are mostly made up of hydrogen and helium. And please label this in your reference table. The first four planets closest to the Sun, Mercury, Venus, Earth, and Mars, are terrestrial planets. And the last four planets closest to the Sun, Jupiter, Saturn, Uranus, and Neptune, are Jovian planets. Remember this. So, and write this down in your note packet. The two types of planets are Jovian and terrestrial planets, and you can find them in your reference table, page 15. Make sure you're labeling them. And one thing you need to know about how these planets formed is something called chemical fractionation. And this is the separating of planets into layers because of density differences early in its formation. What does that mean? So we already know the Earth has many layers. It has a metal core made up of iron. It has a outer core as well. It has a mantle, the crust. But this is not the only planet that has an layers. All the other planets in our solar system also have layers, and this has to do with gravity and density. So when the Earth and all the planets were just forming around the sun, it was really hot and everything was not completely solid yet. So around that time, things were still kind of almost liquidy, and because of this, the more higher density materials that were forming our planets sank to the center of the planets, kind of like our Earth's core with the iron, because of gravity. And the lower density materials, such as silica, started to rise to the surface, and that's formed our crust and all the crust of other planets as well. That's why for most planets in the solar system, or all of them even, the crust or the outer part is normally lower density, and the middle or central part of the planets are higher density because when they were forming, the higher density materials sank to the center because of gravity. So we can see this on Earth, Venus, Mars, Mercury, and even the Moon. This is mostly normal with terrestrial planets because it's not mostly made up of gas. There's rock and metal in it, and normally the central part is the core, which is the highest density, and the outer part, the crust, is lower density. And once again, this is called chemical fractionation. And write this down. Planets have layers. They are caused by gravity and density differences. And that's it. Thank you.